All right, so number 200, page 187 in chapter 2, a noiseless 4 kilohertz channel is sampled every 1 millisecond. What's the maximum data rate?
We're going to use the 2B log 2.
Well, let's write down our information. It's regular word problem stuff, right? So we have a 4 kilohertz channel, and it's sampled every 1 millisecond. What's the maximum data rate? It's noiseless.
It's going to be 8,000 bits per second. 8,000 bits per second, yeah.
So it samples. You can sample it, right? A maximum if you use Nyquist, right? You can sample it 8,000 times a second. But that is samples, not bits.
I mean, I'm just looking at the maximum number of bits per second that you can get down a channel. Bandwidth times the log of 1 plus the signal to noise ratio.
The signal to noise ratio is what? Is infinite.
Yeah.
The signal to noise ratio is infinite because it's noiseless, right? So what's the first part of the question is what?
Infinity.
Right? It's limitless, right? Now, if we put a signal to noise ratio in there, here, what if I said this? If I did the exact same question, say a noiseless 4 kilohertz channel is sampled every 1 millisecond, what's the maximum data rate with sampling of level 2? If I said that, right now I said that sample, remember we talked like our signals, right? Right, there's two levels here, right? Yeah. So a level 2 signaling is binary, right? If it was binary, now we're back to 8,000 because it's log 2 of 2, which is 1, right? So if I give you a level, then that limits it, right? I gave you more information. But if I don't, if you can have an arbitrary sample size and you put however many bits you want in there. So now, if we change the signal to noise ratio to 30 decibels.
Wait a second, I'm not following. What's the formula we're using? Is this the,
so this is,
log 2?
yeah, this is,
And how did we get 8?
Nyquist, right? So Nyquist is, because in a waveform, right, the maximum number of samples is 2 in one wave. Right? If you sample it more than that, you don't get anything else out of it. Right? So it's 2 times the bandwidth, and that bandwidth is a physical bandwidth, not a data bandwidth, right, in hertz. And then what?
Log of SNR.
Log 2 of your sample size, right? I think in the book they call it V or something, but we call it S. Right, but it's of your sample. Because in order to get 2 bits, right, we have to have 4 levels, not right? No.
So the S is the sample, because in the book it says the discrete levels. It says that the V is actually the discrete level.
Yeah, it's the leveling, right? It's whatever your sampling size is.
2.
However many levels are in your sample. To get 2 bits, you need 4, right? To get 3 bits, you need 8 levels. Because you're essentially encoding, right? To get 3 bits, you have to have 8 different encodings to get that. All right. So now, if we change it to 30 dB, we change it to 30 decibels, what formula do we use now? Yeah, Shannon's capacity, right? Because Shannon is the one that came out and said, hey, this is signal to noise ratio, right? So decibel is a measure of signal to noise ratio. So we need Shannon's. What's the formula for Shannon's?
P log to 1 plus the,
It's what?
P log 1 plus the signal to noise ratio.
Yeah. So it's B log 2, right?
Yeah, yep.
And then it's 1 plus the signal noise ratio. And that's the actual ratio, not the logarithmic representation of, right? So 30 decibels translates to what for signal to noise ratio?
1,000, right? 3 zeros.
Yep, 3 zeros, right? So that becomes 1,000. Everybody understand why that becomes 1,000? So decibels is a logarithmic scale. So you take the signal to noise ratio, take the log of it base 10, and then append a 0. So the log of 1,000 base 10 is 3, right? And then you append a 0, that is 30, right? So essentially, if it's an even number, right, it's not 38 or 30. If it's something that ends in a 0, you can just take that, just truncate that number off, and that's the number of zeros that you need, starting with 1. Right? So what's our answer there? Get a breakout a calculator for that one.
I got 39,868 bits per second.
Yeah. 39.8, right?
I was like,
Yeah, it's 39.8 kilobits per second. You simply, that's your, it comes out in bits per second, right, which was 39,000. Normally we take the, our modifier, the kilo, mega, giga, whatever, and stick it in front of there, so we don't have this really long. So this was just, the math isn't really hard in there. All you gotta do is figure out, okay, what equation am I dealing with, right? In the first part of the question, it was Nyquist, right? And he said, but it's misleading because the question doesn't say sample size. And if it doesn't have a sampling, you can pick however many levels you want, right? In noiseless channel, we could have infinite levels. We can get infinite bytes. We could pack it all in there, right? Decoding it might be fun afterwards, right? Even if the noiseless came out, right? And then the second one gives us a dB, which says that we're going to use Shannon. Is it possible that we need to use both? Can Nyquist ever be smaller than Shannon?
Yes.
How?
I mean, if you can fit like a 4-level signal or whatever into your channel, but you choose to only use one.
Correct. Correct. If you say, hey, this is a 2-level, it has to at least be 2, right? But if you say this is a 2-level channel, i.e., you're translating binary information. It's a binary channel, right? But your signal to noise ratio is awesome, right? Then Nyquist will limit you, because you're only transmitting binary information, which is only 2 times. You can only transmit in a perfect channel 2 times the bandwidth in hertz, the physical bandwidth, right? So you could easily be limited. jumped on a bicycle and went down I-25, the speed limit is 75, but you're never gonna fill that, right? Because you chose to take a bicycle. All right. Let's do number 7. So how much bandwidth is in 0.1 microns of spectrum at a wavelength of 1 micron? So we have another formula we need to know. So we're dealing with spectrum, right? And the spectrum is in a length of 1 micron, right? That doesn't give us a frequency really, right? So if the wavelength is 1 micron, right, what's the frequency of that? So we gotta figure that out. Because we need to get a physical electrical engineering type bandwidth, right? And once we figure that out, then we can show how much that is, right? Because that's all it's asking for is the bandwidth. Not how many days, when it says the questions like this, it's not asking for how many bits you can stick in this, right? It's asking for a physical bandwidth. So what do we have? So there's a couple ways you can go about this, right? And unfortunately, this is why the question is not going to be on the test, because there's the question doesn't specify where that bandwidth is, because you would get different answers. Right? So if we have a spectrum, and right here is 1 micron, right? Is our bandwidth here? Is our bandwidth below it? Or is our bandwidth straddle it? They will give you 3 different answers. So for the sake of argument, let's just straddle it. It said, hey, this is our channel, right? And we have 0.1 micron inside that channel, so let's straddle it. So, if we straddle it, how do we figure out the frequency? We're looking for this part right here. In order to get to frequency, what do we have to know?
Frequency equals speed of light divided by the wavelength, right?
Yeah, so frequency equals the speed of light divided by the wavelength, right?
So divide the wavelength by.
So the speed of light is 3. I told you on the email, instead of using the right, we're just going to use 3 times 10 to the 8th meters. Right, that makes it very simple for us because easy numbers. I'm not trying to get exact numbers. I'm trying to see that you have the process down, right? But it's pretty close anyway. I think it's good out to like almost 5 places. Right. Interestingly, we have these other numbers that help us because we frequently measure things in megahertz and gigahertz, right? So interestingly enough, so if we measure things the frequency in meters or the wavelength in meters, and we're trying to get a bandwidth in megahertz, we get a very easy equation, which is frequency times wavelength equals 300. And your answer for your frequency at that point, if you're measuring in meters and megahertz, comes out in megahertz. Because we just took 10 to the 8th and chopped off 6 of the zeros.
Repeat the last part again.
So the speed of light is 3 times 10 to the 8th, right? In meters per second. The nice thing about what we're measuring here is we you almost always measure in kilo, mega, or gigahertz, right? So megahertz is 10 to the 6th already, right? So we can chop that off and make it 2 and make our, instead of having our answer in, we can, right? So, we have a pretty simple math problem, even though the numbers are big, right? We had 1 micron, right? What's our bandwidth in between here? So remember, this is a frequency. It's getting faster and faster and faster, right? And we're trying to measure what the bandwidth is in here and here. That's why it's different if we shift it over, because if we shift it one side, it gets slower. If we shift to the other side, it gets faster. If it gets faster, the bandwidth is more. If it gets slower, the bandwidth is less. Right? So we're trying to straddle this line. So what's our lower bound? It's 0.1 micron, right? We're at 1 micron. So it's 0.95 microns, right? What's our upper bound?
1.05.
1.05, right? Okay, I want to clarify the question here. Since we're going to, we have our spectrum, right? It exists from here to here, and this is where we said that our spectrum lie at 1 micron, and we want to spread across this over here. So the wavelength down here is longer. It's getting faster and faster and faster and faster and faster and faster and so on and so forth as we go this way. So technically, outside of what we drew in class, right, the wavelength is longer down here. So it's 1.05 over here, and then it is right here, and it is 0.95 right here. So these are our numbers. We have 1.05 microns and 0.95 microns. So we need to turn this into a frequency. And remember, what we drew up on the board for frequency was that frequency was equal to the speed of light divided by the wavelength, lambda, right? So these are going to be in our denominators. This is why it changes if we move the spectrum to somewhere else. So it's microns, so this is times 10 to the negative 6th. This is times 10, that's a point there, times negative 6. And then we have the speed of light up here, which is 3 times 10 to the 8th. Same with here, 3 times 10 to the 8th. And then we are going to subtract these and find out the difference. It doesn't really matter what order it is. We're looking for a delta. So if you come out with, if you put them in the wrong order, you can simply take the absolute value, because we're only looking for the space in between them. So when you do that, you work out the math, you end up with 3 over 0.95 minus 3 over 1.05, and that's all times 10 to the 14th, right? This bandwidth is roughly 30,000 gigahertz. This is a wavelength, right?
So you divide 3 times 10 to the 8th by that. Yeah.
That equals a frequency, right? And then if we take C times 0.95 times 10 to the negative 6, that equals a frequency. right? And then we have a range, then we can take this frequency,
Subtract that.
right, and subtract that frequency. So F1 minus F sub 2.
Sorry, I'm going back real quick. How'd you determine 0.95 to 1.05?
So the question was, we're at 1 micron, how much does 0.1 micron, how much bandwidth does 0.1 micron of that have? So the problem is 0.1 micron of bandwidth, depending where it is in the spectrum, has different, it has a different amount of bandwidth, right? So if we shift lower down here, 0.1 micron is really small, right? So if we shift low down here, then it has much less bandwidth, right? If we go up here to X-rays and gamma rays, it has much higher bandwidth, and we all have cancer. So, if we do this, right, so this is 3 times 10 to the 8th divided by this, right, and we do this subtraction. Anybody do the math for that? It's a crazy big number. So if you got a really big number, it's right, probably.
3 times 10 to the 14th, something like that is what I.
Yeah, yeah, it's 3 times 10 to the 14th, right? Three times 10 to the 14th. In our normal way of measuring things in kilo, mega, and giga, what is that?
30,000.
It's 30,000 gigahertz. 30,000 gigahertz of data, or of bandwidth. Even in binary sampling, that is ridiculously big.
So why do we have to break it down into 2 frequencies? Just.
All right, so this is why, right? What if I did the exact same question and put it at 2 microns? Two microns shift it up or down? Right, shifts it down, the wavelength is longer. Right? So then we do 2.05 and 1.95. And what's the bandwidth on that? You might want to do the math. It's not the same number. My intuition is that it's exactly half, 13,000. That's why we have to pick. So now, remember I said we had to make some assumptions, right? Because it said at 1 micron, is that 1 to 1.1, or is that 0.9 to 1, or is that straddle? It would change your answer. Right, and we're dealing with really big numbers, right? So it's not going to. Well, it might be off by a few places when you're dealing in 30,000 gigahertz, right? It's a substantial difference.
So is 3 times 10 to the 14th the entire answer, or just the answer for F1 that we were solving?
So no, 3 times 10 to the 14th is the entire answer. Yeah, if you take the speed of light and divide it by a negative exponent, right, it's going to get bigger, right? And then, in fact, it's going to be really big, which is why the delta is so big. All right. Let's try number 13. This one should be a little easier, other than you gotta look something up in your book. So, on our cheat sheet for our equations, you have to, if you wanna write down stuff for equations, you should probably do that for the cheat sheet. But I won't make you remember where a geosatellite is in orbit, right? So if it's just some crazy number that you have to remember, right, I will provide that to you. So this question says, hey, what's the transit times for a GEO, a MEO, and a LEO satellite? So I would provide you those numbers. In your book, the altitudes are, I know a GEO, or it has the heights in there. So 35,800 kilometers for GEO. MEO is 18,000.
750.
And low Earth is 750. All right. And the question is one-way transit times?
And transit transit.
End-to-end transit time, right? So when it says end-to-end transit time, it's not you're not really measuring the time it takes to get to the satellite, right? Because very unlikely that your endpoint is the satellite, right? It means you have two things sitting on the planet. There's a satellite up there. How long does it take to get there and there?
I was thinking GPS, sorry.
So for GPS stuff, it'd be half, right?
70 milliseconds.
So,
Cheater.
so for the two geos, right? It's 35,800 kilometers high. What's the equation?
You're gonna take the distance divided by the speed of light, I think. Alright.
Divided by the speed of light?
Hold on. Per second, if you wanna have it
So, right, let's do it the old-fashioned physics way and put the, so you have 35,800, right? And for all those guys, this really does help, right?
Another 1,000.
And this is measured in meters, right?
Right. Per second.
And then with speed of light is measured in,
Seconds. Seconds.
So that is 3 times 10 to the 8th.
Per second squared.
Meters per second.
Right, meters per second.
It's
No, meter per second.
Oh, yeah.
yeah, it's meters per second, right?
Mhm.
So that is meters per second,
There we go.
right? So dividing by a fraction, right? So we can take the seconds and put up there, cancel this out, right? And we will get an answer in seconds.
That's what I was thinking.
Take your units and cancel them out. So that way you know what you're at, right? So we're now in seconds, right? So we have 35,800 divided by the speed of light, but we have a transit time of 2.
Well, and
Isn't that that's kilometers?
Yeah, you
So
need
you
to-
gotta do
Oh,
meters.
yeah, it's not-
No,
That's right.
No, the 3
So
zeros.
yeah, multiplied by.
Yep, it should have been kilometers right here, right?
Yeah.
So then we do 1,000, right, meters per kilometer, right, and cancel the kilometer out, and then now we have this meter.
Oh, you wrote 35,800, that's, you wrote it meters.
So it's 35,800 kilometers, right? So times 1,000 meters to make it meters,
Then you gotta multiply the whole thing by 2.
and then you have to multiply the whole thing by 2. What's the quick answer?
0.24 seconds.
0.24 seconds. So it's a quarter second to get there and back. Speed of light's not all that fast.
Just one.
Now, let's do the other one and let's not make it all jacked up. We're gonna do it nice and neat this time. So now we have what? 18,000 kilometers, right? Divided by 3 times 10 to the 8th meters per second. and then 1,000 kilometers per meter, right? Or 1,000 meters per, yeah, per kilometer. So this kilometer cancels out, that kilometer cancels out. This meter cancels out this meter, and this is a divide by divide, so it goes up there, and we have seconds. Right? So now it's 18 times 1,000 divided by 3 times 10 to the 8th, and that is in seconds.
Now, that answer is one way, right?
Right.
That's one way.
We need to double it
And then
to
we
get
just
the real
double
answer.
to get the real answer.
0.1. So it's gonna be all that multiplied by 2, right?
Yep.
0.06 times 2. Oh,
0.12.
1, 2, I guess.
Yeah. 120 milliseconds, right?
Yeah.
And for low Earth, way faster. Guys, can you work out low Earth by yourselves?
$50 milliseconds. I mean, wait, 5 milliseconds.
5.
Yeah, 5.
5 milliseconds. Huh?
What's that?
So this one's a kind of a written out answer, but it should be fairly intuitive. So number 43. Number 43 says, sometimes when a mobile user crosses the boundary from one cell to another, the current cell is abruptly terminated. Even if all transmitters and receivers are functioning perfectly. Why?
Which number was that?
Number 43.
Handoff is unsuccessful.
Yeah.
Why would the
between
handoff be
Verizon-
unsuccessful?
Switch between carriers. Well, that'll happen.
Yeah, that can happen. But what, from a networking perspective, let's
Timing.
not say, it's not a timing issue.
Is it bandwidth?
It kind of is a bandwidth issue, right? So when you're talking to a cell tower, right, you are on a frequency, right? You're in some part of that bandwidth that that cell is capable of talking to. What happens when you move from one cell tower to another?
You change frequencies.
You change frequencies.
Mhm.
What happens if it can't, there's no frequencies available to change?
It just drops.
It just drops you.
Mm-hmm.
You get a call failed, done. It's just a frequency problem.
It could be a timing issue, couldn't it?
Well,
If
yeah.
it's CDMA 2000 or
Yeah, it
some
could
other
be.
protocol.
Yeah, but the most obvious answer is, yes, there are a number of things that
Yeah.
can happen. You can have errors and an uncorrected error and it drops you, right? You could, but the problem is a cell tower can't two adjacent cell towers, right? If they have overlap, they cannot use the same frequencies. Why? Because we jam each other,
Mhm.
right? We would step
Yeah.
on everything, right?
Mhm.
And remember, cell towers are already a mesh network. The towers frequently step on each other, right? Even inside its own tower, like other cell phones can step on it,
Mhm.
right? So you have to negotiate. Hey, I want this frequency. Then the tower has to say, the tower might not say anything because your request for this frequency got stepped on, right? And so then you wait. It turns out that you wait a random number of microseconds before, and all the cell phones agree on this, right?
Yeah.
But it's also why it's easy to jam cell phone towers and easy to jam Wi-Fi, right? Because if you're not playing by the rules and you just make a piece of hardware that just rapidly steps on stuff, you can just completely jam out the entire signal, right? Because those kind of networks rely on everybody playing fair. last one we're gonna do in class. Then hopefully we get to go home early. Number 51. This should be super, super easy. Even though it's number 51.
When they say cable user, are they meaning coaxial cable, or are they meaning STP cable, or are they meaning UTP?
So in the book, in the chapter, this is
They
why I
reference
wouldn't
it
tell you
as-
that. Just presume 27 megabits per second. Because the book was written in 2010, and QDS 128 wasn't in play at that point. So, so assume 27 megabits per second. What's the data rates?
Sorry, can you repeat the question?
Sure. It says, how fast can a cable user receive data if the network is otherwise idle? Assuming the user interface is A, 10 megabits Ethernet, B, 100 megabits Ethernet, and C, 54 megabits per second wireless.
And you said we have to assume 27?
Just assume 27. And in a test, I would tell you that. In
What's
the homework, I
27?
would tell you. 27 is, I believe it's QDS 64. So it was the encoding they used inside, and so it sets the data rate for the cable. So this question is, you can just easily overthink it, right? So you have a cable pipe, right? And it is attached to houses, which normally is a sharing problem and all sorts of other things, right? But it says it's otherwise idle, right? So what is the rate here, if this is our house? It's 27 megabits, right? Then our interface inside our house can either be 10, 100, or 54, right?
So it's just 10, 27, 27.
It's 10, 27, 27. You can't outpace your cable provider, regardless of what you put in your house.
So it's gonna be anywhere between 10 to 27, right?
Now, for the first one, it will be 10 because the lines inside your house are 10. And the second ones are going to be 27 because
Cannot be.
it's always the lowest of the two, right? Your network connection is always the slowest of every link in the chain. So if you have 100 links, right, and some of them have ridiculous bandwidth, if you have something small in the middle,
The max is that small.
then it's that small.
Which is why for the longest time, didn't matter that you had a 100 megabit internet connection inside your, or 100 megabit router inside your house for fast Ethernet. If you only had a 3 meg connection to the outside world, you never got more than 3 meg, period.
Never. Yeah, exactly.
If you were lucky to get the full 3 meg.
Your computers inside your house might be able to talk
Mhm.
quickly, right? But that really didn't come into play until like home sharing and stuff actually became popular.
So I have one quick question.
Sure.
So let's say you're on a phone call and you're in a moving vehicle.
Mm-hmm.
Of course, while the vehicle is moving, there's an handover process going on between different cell towers.
Correct.
Can that lead to an abrupt termination of that?
Correct. It can. Yes. So
Is it that if they don't overlap at all, I mean, if the signal.
they always the cell towers have to overlap. They have to. So let's say you have a cell tower here, and you have a cell tower here, right? And the range is like this. This is a non-overlapping cell tower, right? You're driving down this line, right? You negotiate some frequency, right? And you communicate on that frequency, right? Let's say this for argument's sake, this cell tower is capable of 1,000 frequencies.
Mhm.
So you're in some range of 1 to 1,000, right? Then, if in a non-overlapping cell tower, the nice thing about that is that if you go over here and you were on frequency 1 here, then you can still be on frequency 1. The problem is, right here you terminate your call, right, and you can call again when you get here. Right, so the solution is to put another cell tower here. The problem with that is now we have overlapping frequencies.
Mhm.
What frequencies can we use over here?
On the left, 1 to 1,000, or whatever you have there.
1 to 5, let's just say 1 to 500.
Okay, you're
Right.
not talking different frequency range, okay.
Yeah, so, and then, we're talking about real frequencies, right? 500 to 1,000, right?
Or it'd be
Or
501, yeah.
And then you can use 1 to 500 again, over here. Of course, cell towers aren't linear, right? So they're actually cellular,
Mhm.
right? They look like that,
Mhm.
right? So then, you know, cell tower becomes very placement, and setting the range on the cell tower is also very important,
Mhm.
right? Because you certainly don't want this one to be too close to overlap that one, because then you radically reduce your frequencies.
Mhm.
It's already bad enough. So in this diagram, right, you have overlap for, if you're this guy in the middle, right, you have overlap with 1, 2, 3, 4, 5, 6. So you can only have 1/6 the frequencies that you normally would use.
Mhm.
Otherwise it's still. This is why sometimes when you drive in,
Yep.
you get a call failed.
And it wasn't an issue before we came into digital when it was analog, because you simply just wouldn't disconnect. You'd stay on the other one and get really, really scratchy until you ran out of that signal, and then you
Correct.
would drop.
And then you would
If
drop.
there was nothing else available.
Correct.
And
Yeah. But now everything's digital,
Digital,
right? And
boom.
so scratchy is no longer an option,
Mhm.
because all the information is encoded. And so once you lose the encoding, you're toast.
All or nothing.
It's all or nothing.
Yep.
And we will talk, there's, when we get to networking, there is a lot of information on here, even in Link. I think there's some wireless stuff in Link. Because how do you, this is all a broadcast medium, right? So on a wire, you can do collision detection. In the air, you can't. And so all of these things have to interplay with each other nicely. And who's ever actually used like a radio as a part of their work, like an actual radio?
Mhm.
Right. So normally in fair radio, right, you call out your call sign, right, and ask for air. Somebody gives you permission, and then you talk, and then you say you're done talking.
Mhm. That
Is wireless communications. So the question is, sometimes when we're humans, right, sometimes it doesn't happen often, but sometimes people will key up at the same time and ask for the air, right? And normally there's either nothing in a digital communication, or but you don't get the acknowledgement, right? And then because we're humans, we're like, I'm not sure what's going on, and it's very unlikely that we key up again at the same time. Right, but computers timing is very fast, right? So we have to have some kind of algorithm that says, hey, we're gonna wait some random number of seconds in between here and there, and then ask for the air again, and that's how it works. And there's actually a lot of work going there. It's amazing that on these dirty channels, remember I said that the 2.4 and 5 gigahertz bands, the reason they were given to us by the government is because they were worthless. or at least they were thought they were worthless, right? And so it was all that innovation that came in, and so there's a large body of knowledge that actually goes in to just that communication method.